Okay, so let's continue. Now, as you might have noticed at ping pong, the reading instructions for the physical layer is not in the main book. It's in some other books, which are there are links to those on ping pong. And by the way, I apologize a little bit for the messiness in the week plan on ping pong. I will try to make it a little bit clearer during the weekend or in the coming days, so it's clear to what's going on. But one of the main books used for the physical layer is this a book by Barry, Lee and Messerschmitt. BLM, okay. By the way, you don't need to buy this book. It's available in electronic form, right? So you have PDFs and so forth. So, don't go and buy this. It's available for free. The notation for pulse amplitude modulation here is something like this. It's similar that you have your input amplitudes like this, but they simplify and just write GT here. And then the output is, as before, sum of K, AK, GT minus KT. So it's implicit, capital T is not explicitly noted here, and they don't write pulse amplitude modulation either, as I do. Anyways, otherwise it's the same. Okay, now a quick review of things is that linear time invariant filters. What are those? Well, first of all, linear systems are systems that satisfy the superposition principle, meaning that if x1 produces y1, x2 produces y2, then a linear combination of x1 and x2, that is, we take two scalars, a1 and a2, multiply them with x1 and x2, add everything together. Then if the system is linear, L for linear here, then the output is the same linear combination, but of the corresponding outputs. So x becomes y, like this, and then the scaling factor in front of that is preserved. So this is the superposition principle. Time invariant means that if x produces y, a time invariant system, Ti, is that if we delay the input with tau seconds, then the output to that is the output we get by not delaying and delaying by tau seconds. Okay, so there is an input delay becomes an output delay. Okay, so that's time invariance. So essentially, a time invariant system is something which doesn't change its property in time. That's it. Okay, it's no aging. Okay, and if we put everything together, we have linear and time invariant systems, and then the output of that is the convolution of the input with the impulse response. So what is the impulse response? Well, it's if we take a Dirac delta pulse, which is an infinitely thin, infinitely high pulse, and send that through the filter, we get the impulse response H. Then for any input X, the output is the convolution of the input with the impulse response. Okay, so that was a super quick review of that. This should be known to you, hopefully. Now, so why do we do this? Well, we want to do this because one thing that we would like to do is to filter this signal S of t. So if we have a pulse amplitude modulated signal, filtering of that is also a pulse amplitude modulated signal, but with another pulse shape. So if we have a linear time invariant filter f of t with impulse response f of t. Okay, so this is linear time invariant. Okay, and we have input output like this. So if the input to this is g of t, the pulse that we are using, then the output is h of t, okay, which is g of t convolved with h of t. I immediately apologize because here h of t is the impulse response. But let's not say that h is always the impulse response. It could be anything, right? It should be clear from context here. So here the impulse response is f, and therefore the output, let's call it h, is the input g convolved with, okay, maybe I should write the right thing here then, f of t. Okay, sorry. Okay, so if I then take ak times g of t, what is the output then? Well, since it's a linear filter, the output is ak times h of t. Okay, g gives h, ak times g of t gives ak times h of t. Okay, so that's just the linearity of the thing. Now, if we take the full pulse amplitude modulated input, which is the sum over all k, ak, g, t minus kt. What is then the output? Well, it's a sum due to linearity with the same amplitudes, ak, and then the response to g of t minus kt, which is h, because g gives h, and then it's delayed by kt seconds. So the output is h of t minus kt. Okay. So if the input is pulse amplitude modulation, the output is also pulse amplitude modulation, same amplitudes, different pulse. Okay? And the pulse we get from the output is the convolution of the basic pulse in the input process and the impulse response of the filter. Okay? All right. So this is summarized on this slide, so I won't spend much more time on that. And the reason why we want to do this is the following, because we have now talked about the modulator. Let's talk about the demodulator, the receiver. Okay, so a receiver structure, a very common receiver looks something like this. So here we have the transmitter as before. We have some input symbols, which depends on the input bit, so it's not shown in the diagram here. Produces an output signal. There is some noise, and here we have the receive signal. And the first thing we do, almost always, is to filter the received signal, and that is to suppress noise and different things. Okay, so we feed that through a filter which has impulse response f, and then we get an output y. And once we have this output y, we, for some reason, which is not clear now, but we sample that every t seconds to get an output y of k. And ideally, we would like yk to be equal ak. Right? That would be nice, because what we do then is that we have transferred ak to here without any errors. And once we have ak, we can demap that into the bits that corresponds to that amplitude, and we're done, right? The error-free transmission. So this is what we strive for. And how do we want to achieve this? Well, we want to do that by designing this filter in a smart way to ensure this. Okay. Now, it turns out that that is not possible if the noise is non-zero. But if we assume that the noise is not there, then we should get this, okay, for sure. I mean, if there's no noise, why should we ever make an error, right? So that should be possible, and it turns out to be possible also. Okay, so how to do this is essentially to look at y of t here. So what do we know about y of t? When we know that y of t is sum over k, ak, and then h of t minus kt. This is what we have seen here, right? Okay, and then there is some noise also, like this. But let's for simplicity ignore that for the moment and see what the output is. So the noiseless output when R is equal to S, what is that? Well, it's Y evaluated when small t is equal to K capital T. So in this formula here, we replace small t with K times capital T, and then the following result follows. Okay, so maybe I should write this up. Y, K, T. Okay, so what is Y? Well, it's the sum over all K, A, K, H, T minus K. Sorry, rookie mistake. I will do this again. I will sum over some other variable M, A, M, H, T minus capital M, T, like this. Okay. Of course, this is equal to this, right? It doesn't matter that we sum over M or K or L or Z or whatever, right? It's just a summation variable, okay? It doesn't matter, okay? So here we choose this as M. And the reason why I choose M here is because I don't want to confuse it with the K that we have here. Okay, so this is Y of T. And then we would like to set in small t equals K capital T. And what we get then is the sum M from minus infinity to infinity, A, M, H, K capital T minus M, T, like that. Right, I just replaced small t with K times capital T. And if we look at this, this is H, K minus M capital T, like this. And this we can split out by taking out the things we're interested in this right-hand side, Y of K. What we would like to do is to make Y of K equals AK, right? So we take out the AK term here, AK, and we see that that is multiplied with H0, right? When M is equal to K, we have K minus M is K minus K, which is 0, right? So then we get this, and then we get a sum of the rest. It's the sum over all M, except when M is equal to K of AK, H, M minus K, capital T, like this. All right. So what we would like to do then is to make Y of K equals to AK. Okay, and this we can do. It's equal to AK if H of 0 is equal to 1. Okay. So let's just make H of 0 equals to 1. But then we have this term here that we would like to get rid of. Okay. As a matter of fact, this is known as an interference term, or to be more precise, as inter-symbol interference, or ISI. And why is it called inter-symbol? It's because the interference comes from other symbols. So we're interested in the kth symbol, but the interference comes from other symbols that we are not interested in at this moment in time. Little bit later, we might be interested in those, but at time k, we are not interested in these. So ideally, we would like this sum to become 0. So how do we make this sum 0? Well, it's a product of amplitudes and pulses. The amplitudes we have no control over. That carries the data. So the only way we can make this equal to 0 for all possible input amplitudes here is to make all of these samples of the signal H equal to 0. So this is all 0 if samples of the pulse is equal to 0 for all integers L, except when L is equal to 0. Okay, so let's make an example to see when this is the case. ideally, we would like to make h of nt equals to 1 when n is equal to 0, and 0 when n is plus minus 1, plus minus 2, etc. Okay? So, for example, if we choose to use a pulse g, and for simplicity I just make it centered around the origin. It's not important, but I'll do that anyways for simplicity only. So something that looks like this. Okay, and let's make this equal to t over 2 and this negative t over 2. So the duration of the pulse is t seconds. Yeah, for some reason it's like this. And then we convolve that with a filter f of t like this. So f we can choose. And to make life easy for me, I choose it to be exactly the same as g. And if this has amplitude 1, I will, for simplicity, just choose the amplitude 1 over t here. Okay, and the amplitudes are not super important. The shapes are more important here. Okay, and if I convolve a box with a box, what do I get then? There are a few convolutions one should maybe memorize. So if I take a square pulse and I convolve it with itself, what do I get then? Triangular pulse, correct. So we will get a triangular pulse here. And it will start at time minus t and end at time capital T, like this. And since I've chosen this amplitude smart enough, it turns out that the midpoint here would have amplitude 1. Okay, so is this ideal? Yes, it is, right? Because we have 1 when n is equal to 0, we have 0 when n is equal to 1, we have 0 when n is equal to 2t, when t is equal to 2t, and so forth to the right. And we have 0 here for negative t, and of course 0, like this. So this is ideal. Okay. One can show, and it's not hard to show, is that as long as the pulse that we're using is confined to a duration of t seconds, where t is the time when we can the time between pulses, and the receiver filter is likewise also limited to duration t seconds, then we will get 0 points like this, and we will get some amplitude here. Not necessarily 1, but it's some amplitude at least. And it doesn't really matter what that amplitude is as long as it's not 0. We can always compensate for this later on. Okay? So as long as the duration of the pulse that we use for transmission and the duration of the impulse response is also limited to t seconds, we will always be able to do interference-free transmission. Objective obtained. Okay? So it actually turned out to be not so difficult. Okay. So are we done? Unfortunately not. Okay. And the reason for this is that very often we would like to make the transmitted signal band limited. Okay. It has to be confined in frequency. And the reason for this is that the transmission medium might not be conducive to all frequencies. It might have band limitations. Or if this is a wireless signal, it's very important to keep it confined to its channel, right? Otherwise, it will create too much interference with other things. So we would like to achieve this interference-free transmission under the condition that the bandwidth of the transmitted signal, is band limited, which is the same thing to say that the pulse that we use needs to be band limited. And it's an unfortunate fact of life that no time limited signal can be band limited. Okay? So a band limited signal will extend forever from minus infinity to infinity. Okay. So can we still achieve interference-free transmission in this case? And I can tell you the answer is correct, but we need to do a little bit more work. The answer is yes, but we need to do a little bit more work. Okay, so first of all, what is bandwidth? And here is extra important in a course like this to distinguish bandwidth, what we as electrical engineers typically talk about, and what people that do data communication typically talk about, because they talk about bandwidth as data rate, the number of bits per second that you can transmit. So if you read the book, you might see, or read Google or whatever, when people talk about bandwidth, they sometimes mean data rate, bits per second. While here, bandwidth, we talk about the bandwidth I'm talking about here is the signal bandwidth, which is measured in hertz. Okay? And that should not be confused with data rate in this context. Okay? Now, it turns out that if the pulse G has a spectrum, G of f, we say that this has a certain bandwidth, absolute bandwidth, if the difference between the highest and the lowest positive frequency, that's the bandwidth. Okay, so bandwidth for a baseband signal, which has most of its energy centered around 0 hertz, is counted from 0 up to the highest frequency component here. Bandwidth for a passband signal, which has its power centered around some mid-frequency, which is not 0, then it's the difference between the lowest positive frequency, which is this one, and the highest frequency component, which is this one. Okay. So bandwidth here is somehow twice the bandwidth here, if you like. Okay. But don't think about it like that. Rather think of it as the difference between the highest and the lowest positive frequency component in G. You will always be fine. Okay. Now, is the literature consistent on this? Of course not, right? So sometimes one talks about double-sided or single-sided bandwidths, and there are many other bandwidth definitions out there. So again, you need to be careful when you read books to figure out when they talk about bandwidth, what do they actually mean? Okay. Now, okay, so we continue here. And if there is anything from this part of the lecture that you need to spend time on, is this slide. Okay. So this is super important because it has the conclusions, and then later on we will support these conclusions with some derivation. Right. Now, suppose that G, the pulse that we are using to create the transmitted signal, has bandwidth W. Okay, so it has this W if it happens to be baseband signal, or if it's a passband signal, it has this W. Okay. Now, if that is the case, then the following is true. If the symbol rate, which is determined by T, so the symbol rate is 1 over T, and it's measured in symbols per second. Okay. If the symbol rate exceeds twice the bandwidth of W, okay, so think of it that we fixed the bandwidth of the pulse here, and we change the symbol rate. If it's too high, that is greater than twice the bandwidth, then there is no way we can have intersymbol interference-free transmission. Okay. So that's unfortunate. So that is the case. Now, if we completely on the border here, that the symbol rate is exactly equal twice the bandwidth, then we can have intersymbol interference-free transmission if, and only if, G convolved with F is this sinc function. Okay. That's the only possibility. if the symbol rate is less than twice the bandwidth, then it's possible to do inter-symbol interference-free transmission, and for many choices of G convolved with F. Because, again, what determines if we have inter-symbol interference-free transmission is properties of H, right? And H depends on the pulse we have chosen to use at the transmitter and the impulse response we have chosen to do at the receiver. So the combination of these two things needs to be good. Okay. So here we are free to choose, oops, I don't want to do that. We are free to choose G and we are free to choose F. The only constraint we have on G is it has to have a bandwidth W. It's band limited to W. Okay. So can we choose G and F to have inter-symbol interference-free transmission? And yes, we can do that in the lower two cases and no in the upper case here. So essentially it's like this also, that you think that if we have a certain bandwidth of the transmitted signal, the higher the data rate is, that sometime after a while we run into trouble. Okay, so that is sort of reasonable that that would be the case. Okay, any questions so far? No. Okay. So how does this? Why can we have here inter-symbol interference-free transmission for any t, right? And that has to do with the case that this is not band limited. So G of t is not band limited here. So that's the difference. As soon as we go to band limited signals, G, then we have, it's more difficult actually. Okay, now, so lecture quiz. Suppose we have pulse amplitude modulation. Okay, we have a pulse has a bandwidth of 1 megahertz. Okay, what is the maximum symbol rate we can use without introducing inter-symbol interference? Okay, maximum symbol rate, bandwidth 1 megahertz, pulse amplitude modulation. So I'll give you 10 seconds to think about this. Okay. So how many for A, B, C, D? Yeah. Okay. So the correct answer here is we can transmit with at most twice the bandwidth. Okay, and it's in symbols per second, not bits per second. Okay, remember that the symbol can carry many bits. It's unclear to us, right? So the only constraint we have here is on symbol rate, not on bit rate. We will return to the bit rate later on. Okay. So what is the maximum data rate? Here, I'll give you 10 more seconds. Is it 1 megabit per second, 2 megabit per second, 2 megasymbols per second, or none of the above? Right. Very good. None of the above, right? And the reason for this is that the maximum data rate is not determined by the bandwidth only. It is very much dependent on bandwidth, as we will see later on, but there are other factors in play also. Okay, so we'll return to that. Okay, Nyquist pulses. So here is a picture of Harry Nyquist, and the only reason I have it here is because he happens to be born in Värmland, so it's a Swedish dude. That spent most of his professional life in the United States. Okay, so maybe we should call it Nyquist pulser, but it's Nyquist pulses, typically, people say. Okay, So what is a Nyquist pulse? Nyquist pulse is an ideal pulse in the sense that we have no intersymbol interference. Okay, so a signal is a Nyquist pulse if it fulfills this requirement. Okay. And the requirement is that if we take evenly spaced samples of h, we get one which is equal to 1 when k is equal to 0 and all others is 0. So this is a Nyquist pulse, this triangle. There are other Nyquist pulses, of course. I mean, any pulse I can draw that has the correct zero crossings. Now I draw a little bit different. This is also a Nyquist pulse. Or this is also a Nyquist pulse. Okay. So the only thing that we say is it has to go through 1 here, 0 here, 0 here, 0 here, and so forth, right? So that's a Nyquist pulse. Okay. It turns out, and we will motivate this briefly, that if this is the requirement in the time domain, we have the following requirement in the frequency domain, namely this one. Okay, so it looks a little bit more complicated, but it's actually quite insightful. We can draw a lot of conclusions from this. So what does it say? It says that the Fourier transform, so small h has a Fourier transform capital H. If we take capital H as a function of frequency, and we essentially form a pulse amplitude modulation process of this with amplitude 1. Okay, so we take h and we repeat that on the f-axis, spaced by 1 over t, multiples of that. Sum all of these together, scale with 1 over t, we get 1. Okay. So, and the equality here follows from the sampling theorem, and then capital H here is the Fourier transform of small h. Okay. So I won't explain exactly how this is at the moment, so just trust me. It's not very difficult to show, but it takes 5 minutes. Okay, so I'll prioritize that for the moment. Okay, so an equivalent statement is that we still have this time domain thing, but we can also write this as here. And the only thing we have done is that we have multiplied this with t, and t is 1 over rs. Okay, so this is the same statement here. Okay, so now what we want to do is to investigate this. If this can tell us something that can allow us to conclude this. Okay, so the objective now is to study this criterion to be able to conclude this. Okay, so let's set this up. A connection between intersymbol interference bandwidth and symbol rate. If G is band limited, then H, which is G convolved with F, is also band limited. Why is that? Well, H is the convolution between G and F, so if we take the Fourier transform of this, capital H is equal to G multiplied with capital F. Okay. Convolution in the time domain is multiplication in the frequency domain. Now, since G is band limited to W, it's something that, I don't know, like this maybe. Then if we take G and multiply that with any other function, for sure that function would be 0 outside negative W and W. Simply because G is 0 then. 0 times something is 0. Okay. So H is band limited. Good. So the question we had to show that H is a Nyquist pulse is to see whether it fulfills this requirement. So if we take H and we repeat that, we form this sum, it should form a constant. So it should be a constant as a function of F. So this line here is this constant. Okay. So what we want to do then is to plot H, put that out and add it together and see whether it adds up to 1. If it adds up to 1, it's a Nyquist pulse. If it doesn't add up to 1, it's not a Nyquist pulse. Okay? Okay, so let's do that. First thing we do then is to put in the first pulse here. Okay, h of f. So that is for k equals 0. Then we put in the other pulses. So we take h and we shift it to the right rs, shift it to the 2rs and so forth, and to negative rs, and we add them together. So right now I can ask you, is this a Nyquist pulse? If this happens to be the spectrum, is this a Nyquist pulse? I see some people nodding their head. Of course it's not, because if I add all these pulses together, I don't get the top line. I get something, you know, a bunch of triangles. It's certainly not a constant, right? So it's not a Nyquist pulse. Okay, so let's continue. We realize that there is a gap here. Okay, and let's specify this gap. We see that since we repeat h of f minus rs is centered around rs, so it starts to become non-zero at the point rs minus w. Okay, because the distance from here to here is w. Okay, and the other pulse starts from 0 and it becomes 0. The other pulse starts here and it goes down to 0 at w. So the gap here is the difference between the top frequency and the lower frequency here. So the gap is rs minus w minus w. So rs minus 2w. That's the size of the gap. Okay? Now, as long as there is a non-zero gap, we would never ever be able to achieve a constant value in the gap, right? So as long as there is a gap here, we can never, of course, add something together. We can't add 0 together to get something which is non-zero. Okay? So as long as the gap is non-zero, we're screwed. There is no way we can do this, right? And there will be no Nyquist pulse. You see the logic? I hope? Okay. So we draw the following conclusion. If the gap is greater than 0, okay, we know that it cannot be Nyquist. Okay? If the gap is 0, that's the same thing to say that rs minus 2w is greater than 0, which is the same thing to say that rs is greater than 2w. Okay, so here's our first conclusion actually. From the Nyquist criterion, we see that if the symbol rate is greater than twice the bandwidth of the transmitted signal, then we can never avoid intersymbol interference. All right, so let's continue then. If the gap is equal to 0, that is, if we close this gap, then it's actually possible to do intersymbol interference-free transmission, but only if the spectrum of the transmitted signal is a box, right? Because then these boxes will perfectly butt up against each other and form a constant. Okay. So if the Fourier transform of a box, what is the inverse Fourier transform of that? That's a sink. Okay. So it is possible to have intersymbol interference-free transmission, but only if H happens to be a sink. That's the only choice we have. Okay. Now, if the gap is less than 0, then we don't necessarily need to have boxes anymore. We can have other shapes. And as a matter of fact, there's infinitely many shapes we can use then. So then we have some design freedom. Right? Of course, not all choices are okay, but there are many choices, infinitely many choices which are okay. Okay, so now, summarizing these 3 rules, we have motivated why the top level where I said, okay, this is what you need to know, right? That has been motivated now, and it has been motivated through the Nyquist criterion. Okay, So let's continue now. And OK, so by the way, this last setting is typically what we use in real designs, since in 3G, for instance, this is used. OK, so we continue now and look at a family of pulses which fulfill this requirement. OK, now the pulses that I will present now is not super important in itself. They're an important case or important practical choice of pulses, but they have, I don't want you to memorize these equations. It's not needed, right? But I'll just show them for completeness. Okay, so it turns out that if we have a spectrum that looks like this, which I will show a plot of soon, or inverse transform of that, this is the time signal. So this is the frequency, and this is the time signal. This is called a raised cosine. It's called a raised cosine because if you plot the spectrum, it's a flat line, and then there is half a cosine that goes like this. So if I would continue to plot the cosine, it would go something like this. Okay, so it's a cosine which is raised up. That's why it's called the raised cosine. You know, it's symmetric around 1/2 here. So it has a flat region and then a cosine shape which smoothly takes this from 1 down to 0 here, or from t down to 0. Okay, and the bandwidth of this is determined by this factor. So the bandwidth depends on a parameter alpha. And alpha we can choose to between 0 and 1. Okay, it's something that it's a design choice. Okay, then one can see that the bandwidth here, W, is 1 plus alpha over 2t. And we can split that out to be 1 over 2t plus alpha over 2t. And if we think about that a little bit, that we continue to write this. This is 2 times r plus 2 times r times alpha. Rs, the symbol, right? Okay. So this is the smallest bandwidth we need for intersymbol interference-free transmission, while this is the extra bandwidth that we use. Okay, so the later here is called the excess bandwidth, and the amount of excess bandwidth clearly depends on alpha. So by doing alpha a little bit, we sacrifice a little bit in bandwidth to get intersymbol interference-free transmission. Yes. And why is bandwidth important? Well, it's because in many cases we would like to transmit as many symbols per second. Let's not go down that path today. We'll take that on Monday. But I have a few other things to show also. Okay. So this is how it looks in time domain. It's sort of sync-like. Sync, you know, it's okay. Maybe I wasn't very explicit, but sync of t is sine pi t over pi t, right? Okay. And if you remember how sync looks like, it goes up and down like this. As a matter of fact, if we choose alpha equals to 0, then the raised cosine pulse is a sync. Okay, so let's see, it's a little bit hard to see, but the blue path here is the sync. If we choose alpha to be a little bit larger, then we see that the side lobes of that pulse shrinks down a little bit. Okay, so that's the effect of choosing alpha greater than 0. And if we let's say it's enough for this week, and we'll continue with this a little bit on Monday, very quickly over root raised cosine pulses and so forth. So yeah, have a nice weekend. See you on Monday.